Hello, and welcome to the Practical Engineering Solutions channel. My name is Jack. Today we're going to talk about how to make a transistor switch for model railroad applications and many other uses as well. First, the advantages of using a transistor switch. Reliability. There's no moving parts or contacts or anything to wear out. It's all solid state. So that's a big problem that you can avoid. Also, transistors use small voltages and currents to control much larger voltages and currents. And, of course, transistors can operate much faster than manual switches, and they can be automated. There's two types of transistors we're going to talk about today. Primarily, the first one is bipolar, but there also are MOSFETs, and we're going to do that, and we're going to talk about that in part 2. There are several different types of bipolar transistors. General bipolar transistors are broken down into NPN and PNP, and we're going to focus on those. We're not going to talk about the bias resistor built-in transistors or the radio frequency RF transistors. Before we talk about transistors, we need to have an understanding of diodes. So this diagram shows diodes, both forward biased and back biased. When a diode is forward biased, the plus voltage is on the anode, the minus voltage is on the cathode. When this occurs, the diode is said to be conducting, and there's about a 0.6 to 0.7 voltage drop across a typical silicon diode. When the plus is on the cathode and the negative voltage is on the anode, that's considered to be back biased or non-conducting. General purpose bipolar transistors have what it looks like a sandwich of N material, P material, and N material. And this is a typical NPN transistor. The characteristics or the terminals are called the emitter, the collector, and the base. And the only difference between NPN and PNP is the polarity. Now this is how they look on a schematic diagram with the base, collector, and emitter identified. The one we're going to focus on today is an NPN 2N2222, but a PNP 2N2907 is the PNP equivalent of the 2222. So let's describe an NPN transistor and how would we look at one and test it. An NPN transistor can be thought of as two diodes back to back. And you see here the collector is at the junction of the two diodes. I'm sorry, the base is at the junction of two diodes, then there's a collector and emitter. This is a typical package of a 2N2222 plastic TO92 type package. Looking at it from the bottom with the flat side up, the emitter is on the left, the first lead, the base is in the middle, and the collector is on the other lead, on the right. So how do we test an NPN transistor? Well, pretty easily. We take an ohm meter and we put a plus voltage, the red lead, on the base, a negative voltage, or the black lead, on the collector, and we should see some resistance. Then we check the back bias by putting a plus on the collector and negative on the base, and this should be very high resistance or no connection. So that way we're checking the base collector diode, both forward biased and reverse biased, or back biased. Third step, we do the same for the other diode. Put plus on the emitter, negative on the base, and we should see a very high resistance because it's back biased. Then step 4, we take a plus lead, the red lead, put it on the base, the negative lead on the emitter, and we should see some resistance. Okay, so why are we going to use a 2N2222? Well, for this example and most examples, it's a very popular transistor. It's NPN, which is more popular than PNP. It's widely available. It's inexpensive. I bought 200 of them on Amazon for about $6. And it's easy to find data sheets online, multiple data sheets from multiple manufacturers, very easily to pull up. It also has good characteristics and it's very well documented. Okay, step 1 is to determine the amount of current you require or need for the transistor to control. In this example, we're going to use a hypothetical LED that consumes 100 milliamps of power. This is a super LED. And on the right, you can it shows the conceptual idea of what we're trying to do here. You have a small base current coming into the transistor and controlling a switch, basically, a larger current going from the collector to emitter. And we're saying again, this is 100 milliamp maximum. It can be any other current. It can be one LED or 5 LEDs or a motor or a relay, whatever you require. Okay, so that's step 1A. Just remember that we still have to limit the current to the LED. Any LED, which is a diode or regular diode, must have a resistor to limit the current, or the diode will go boom. Okay, next is step 1B. This is to determine the current gain. And we need this to decide or figure out how much current we put into the base. So if you look up on the data sheet, HFE, which stands for current gain. I have no idea why they used HFE as a symbol. But anyway, it's the collector current over the base current. So if the base current in the transistor is 1 milliamp and the collector current that we are planning on or figuring on is 100 milliamps, that's a 1 to 100 ratio, and we say the current gain is 100. Now, the problem is in the data sheets, it has HFE, but it's listed for a lot of different things that have nothing to do with transistor switch. It has most of the time the HFE, or the current gain, is quoted based on amplification, using the transistor as an amplifier. So it can be very confusing because it depends on how it's used. The current gain depends on the temperature and a whole bunch of other stuff, the collector current. So I like to use this graph, and it's in some of the data sheets, not all of them, but it's very easy to understand, and let me just quickly go through it. The HFE, or the current gain, as I mentioned, depends on the collector current requirement. So this curve is for 1 milliamp, this curve is for 10, this curve is for 150, and this curve is for 500. So we said 100 was our goal, and the 150 is pretty close to the 100. So this says that if we put in 3 milliamps of base current, we will get along this curve 150 milliamps of collector current. So if we put in 3 here, and we get the 150, this is a 150 curve, the ratio between 150 divided by 3 is 50. So the current gain here is 50. Same transistor, but if we were using it only 10 milliamps collector current, we put in 0.3 milliamps, the current gain here would only be 33. So we're going to use 50. It's close to what our requirements are. And you see this little flat line here. This says that the transistor is in saturation. What does saturation means? That means that if you increase the current even more, it's not going to, the voltage on the output is not going to get any lower. It's going to stay the same. So no matter how much collector current base current you put in, it's still going to be in saturation, only more in saturation. It's basically flatlined. So again, this axis here is the collector to emitter voltage. This tells you how good a switch it is. Do you have 1 volt across that switch? Is it dropping 1 volt, or is it dropping much less? Like in our case, it's dropping at this line here, this horizontal line, it's dropping 0.1 volts. That's pretty good. That's pretty good. So we got a gain of 50, a collected a base of about 0.1, and we know it's in saturation mode because any more base current's not going to reduce the voltage across the collector and emitter. Okay, so step 2, determine the base current. Well, how do we do that? Well, don't forget there's a 0.7 volt drop across here. So we'll figure that we're putting in 5 volts. There's a 0.7 here, so across the resistor is 5 minus 0.7. And we know that the current gain, we said before, is 50 at the saturation voltage. It's much less than 1 volt, the saturation voltage, with 150 milliamp collector current. So 2 milliamps into the base emitter junction will provide a minimum of 100. How do we get that? We just took 100 and divided by 50, get the gain, and we say we need 2 milliamps flowing through this resistor. So all we do is use Ohm's law, I equals E over R, or in this case, R equals the voltage over the current. We subtract the 0.7 volts drop from the supply. So it's 5 volts minus 0.7 volts, which is 4.3 volts, divided by 2, is 2200 ohms. So there we have calculated the base resistor. It'll allow 2 milliamps to flow through the base emitter diode, and that, because there's a gain of 50, will allow 100 milliamps to flow from the collector to emitter. Okay, so that's a good circuit, but there are some issues with it. First of all, it uses 2 voltages. It uses a 12 volt voltage up here. It uses a plus 5 volts to trigger the transistor. Also, when there's no voltage here on this 5 volts, if that happens to be disconnected on purpose or it's just 0 volts, the base could be subjected to noise, and the noise could trigger the transistor accidentally. So we really want to make sure that when there's no voltage coming into the base over here, the base is tied to ground. Also, we're gonna figure out, as we did before, the voltage drop across the collector and emitter, and of course we need a resistor for the LED. Here's step 3. This is a more practical circuit. Why is it more practical? Well, it uses 1 supply voltage instead of 2. It ties the base to ground to shut off the transistor, and we need to do that, as I mentioned before, because if this switch up here is open and there's no voltage going through this resistor, the base is essentially floating. And this resistor ties the base to the emitter and ground and prevents the transistor from turning on. Also, we're going to figure out the voltage drop across the collector, as we have shown before, and we need a limiting resistor for the LED. So first thing we're going to do is calculate the base resistor with the new voltage. Same calculation as before, no difference. Only difference is there's a 12 volt supply now instead of a 5 volt supply. So as a result of that, the new resistor value is 5600 ohms, which will allow 2 milliamps to flow in the base, and that will cause 100 milliamps to be available for the transistor collector emitter junction. Second thing we're going to do is figure out the value of this resistor, the base emitter resistor, and that can be anything between 1K to 1 meg. And it basically, as I said before, it'll keep the transistor shut off when there's no voltage at the base. Next thing is, as we saw from the curves, the HFE curves I showed you earlier, there's about in our situation, about a 0.1 volt drop across the collector to emitter. That's again called VCE sat, the saturation voltage based on those curves. So together, between the LED drop of 1.8 volts here, the 0.1 volts drop here, we have a total of around 2 volt drop. And to calculate this resistor, we take the 12 volt supply, subtract 2 volts for the 2 drops, and that resistor has to be 100 ohms. If we wanted to use this as just a 20 milliamp load instead of 100, we would just do the 12 volts minus 2 volts divided by 20, and we get 500 ohms. But don't forget, if you do that and only have a 20 milliamp load, you have to recalculate this base resistor based on the new HFE, which is only 33 when you're using 20 milliamps. So by doing that calculation, you should be fine, and I think this resistor will come out to be much higher value. Other than that, everything should work. Okay, step 4. The last thing you want to check is the maximum ratings. I want to make sure you're not stressing this transistor too much. So the first thing I look at is the power dissipated across it. And we said that it's anywhere from 0.4 to 1.6 volts, depending on the collector current. In our case, it's much less than that. It's about 0.1 volts. But let's take the worst case if we were using another curve on that chart I showed you. Power dissipated is voltage times current. So let's say it was 1.6 volts times 0.1 amps. It would be 0.16 watts or 160 milliwatts. And you can see here that the maximum rating for the 2N2222 is 625 milliwatts. So we're in good shape there. The collector base voltage, where it could be 60 volts. The maximum can be 30 volts for collector emitter voltage. We're nowhere near that. We're at 12 volts at the most. The emitter base voltage, this is the reverse biased voltage, not the forward biased voltage we used to calculate the base resistor. And that's 5 and 6 volts. We're nowhere near that. Collector current, 600 milliamps. We assumed 100. And junction temperature, 150. It can run storage minus 55 to plus 150. So we're in good shape there. So the bottom line is that a transistor switch, again, can control a large load with a small current. It can be remote from the load, which is handy. It can be for safety reasons or convenience. Different loads can be controlled. You can have LEDs, relays, motors, any kind of a DC load, and use light gauge wiring for the trigger, or the base wiring. Model railroading, you can use it as an interface from a single board, a processor to lighting circuits, switching turnouts or signals. And the 2222 is a very inexpensive transistor capable of significant power handling and DC current gain. So I'd encourage you to try it out. It's pretty simple. Play around with it. Use a prototype board. And thank you for watching this video. If you liked it, please select like and the bell, and please subscribe. Thank you, and see you in the next video.